I'm going to talk about an aspect of superconducting qubits and circuit QED, which Steve actually skipped over, so in some sense in a good way, because I can then concentrate on that. It's actually the measurement aspect. And Steve had told you a little bit about how the measurement is done in these systems. I'm going to go into a bit more detail and tell you about some new advancements in the measurement technology, which is also extremely important, because at the end of the day, you need to be able to measure the state of your qubits. And I'm going to tell you about some recent exciting results on quantum measurement in these kinds of systems. So essentially, there's sort of two main parts of the talk. The first one is about quantum measurements. In particular, I'm going to talk about what are called weak quantum measurements. I will explain in a little bit more detail in the next few slides. What do I mean by that? And the architecture is the dispersive readout, which Steve nicely explained, but with the help of a special kind of an amplifier, a parametric amplifier, which allows us to measure these states very, very precisely without with very minimal loss of information. And then I will show you in the later half of the talk how we can use such measurements to do feedback control. All the experiments you heard about so far in the previous talk were sort of one way, in the sense that you prepare something and you make a measurement. Now what we do is we prepare something, we make a measurement, and then we use the result of the measurement to do something back on the quantum system. And that's the idea of quantum feedback control. And I will explain this experiment of stabilizing Rabi oscillations in a superconductor. So I'm going to start by just briefly reminding everyone, so that everyone is on the same page, the basic textbook picture of quantum mechanics and quantum measurement we sort of learn. I'm going to use the two-level system as an example here. You can create a two-level system using these superconducting circuits, and I can create some arbitrary superposition given by these coefficients alpha and beta, and that's your initial state. And you can represent these states on a block sphere, as Steve had also pointed out, by the position of this block vector on a sphere. Things pointing along there are ground state, things pointing down are excited state. People often change these conventions around, so I like this one better, where the ground state is on the north pole and the excited state is on the south pole. And you can then parameterize the state by two angles, essentially, theta and phi, which uniquely identifies the position of this on the block sphere and the superposition. So, aspect of the most standard textbook measurement is that after the measurement, if we measure the state 0, the system actually is no longer in a superposition state, but it ends up in the corresponding eigenstate of what you measured. So in this case, if you measure 0, the state after the measurement ends up is a ground state, and same for the excited state measurement, where if you measure 1, the system ends up in the excited state. Now, this is a special class of measurements, but typically when we learn about quantum measurements in introductory quantum course, this is the kind of measurement we talk about, and often we call these kind of measurement quantum non-demolition measurements. There is often a controversy on the use of this term, but this is what I mean, that the resulting state is highly correlated or is exactly given by the result of the measurement, and it's not randomized, for example. But in reality, the measurement is a lot more complicated. I just said to you that we measure. What does that actually even mean? In a real experiment, if you start with some two-level system, here I've sort of shown them as some atomic states, the standard process usually is to entangle or couple this quantum degree of freedom to some auxiliary state, which is often called the pointer state. In the example discussed, that auxiliary system is the cavity, or the states of the photons in the cavity. Okay. And it's really, the experimenter is actually measuring what's happening to the pointer state. And that usually involves a series stage of amplifications. You know, here we are talking about microwave signals. We have to take those photons in the cavity, and then we have to send them through several stages of amplification before it can be connected to some meter sitting in our laboratory, which is going to, you know, say that, oh, the result is 0 or the result is 1. This is actually the real challenge in these experiments. And this particular protocol, you know, if you have a two-level system, you would expect to get two answers. But in any real experiment, what you really get are distributions, right? You're not going to get exactly 0. Let's say that this was a voltmeter reading 0 volts and 1 volt. You're not going to get exactly 0 volt and exactly 1 volt. Nominally, you would expect that there will be a distribution around 0 volt and a distribution around 1 volt. I mean, there's always some kind of noise in the measurement. I will be a bit more precise about the nature of this noise in just a little bit. And if you encounter a situation where the distribution of values corresponding to the 0 volts and the distribution of values near 1 volt are well separated as shown here, which means that there is absolutely no ambiguity. Even though I'm not getting exactly 0 or 1, I can draw a line in the middle and I say all values to the left, I will treat them as 0, all values towards the right, I treat them as 1. Then it actually maps back to the picture I described before of a very precise measurement of the state. So all the blue values, yes? That's a good question. So he's asking if it's in principle possible to reduce the noise. The answer is yes, and I will explain some of the challenges of what goes in achieving that. But if you think about it, a single value 0, and you're talking about delta function like results. I mean, of course, that's never possible. It's only a question of experimental accuracy. There is a tail to this distribution which extends over there. Now, if the area under the tail from 0 under what I call 1 here is small enough, so it's always a question of precision. How many 9s do you want in the result? How confident you are that it's 0? Is it 99.99 or is it 99.99%? That's sort of a precise experimental question, and that's what really determines this question. So this could be any quantity you're measuring in your laboratory. It could be a voltage, it could be a current. So yes.
So what is on the vertical axis?
The vertical axis is just a number of counts. So what I'm imagining here is that, let's say I prepare a system in an equal superposition of ground and excited state. I go and make a measurement. The meter is now telling me some voltage, and I basically start making histograms. And after sort of repeating it many, many times, you will get a distribution like this. If you have an equal superposition, that half the weight is in the 0.
Not the resolution error in the
I will come to that in just a second. Okay. So right now, let's say that there is some noise which is coming from somewhere. But the important thing is that if these histograms are well separated, then I can make a very precise statement of what the result of the measurement is. I just draw a line here. All values less than, say, 0.5 volts, I call 0. All values greater than 0.5 volts, I call 1. And I say the result of the measurement is 0 or 1. Okay. But imagine that there is a situation where these histograms look like this. Okay. Now, this could be easily achieved by making a horrible measurement and completely contaminating your signal with noise so that you can no longer able to separate these histograms. But I'm going to talk about a slightly different situation where the overlap of these histograms is not due to technical noise or something bad you did in the experiment, but it's exactly defined by how you did the measurement. And it will become clear later in the talk how we can actually control that. Now, if you actually reach that situation and you do one measurement, you prepare an equal superposition, you do one measurement, you're going to get a result which is going to fall anywhere along this distribution. But now you can no longer say which distribution it belongs to because they are not separated. So what is the result of the measurement? It's actually an incomplete measurement, and it's also known as what's a weak measurement. Okay? So this is the definition. Thank you for asking that question. Aronov's weak measurement and weak values are related but slightly different concept. So these are, I'm not talking about weak values, but in the sense of an incomplete measurement, it's the same idea. But there is often people use these two terms interchangeably, but these are not weak values. Okay, I can answer some of them more detail later on, but these are not weak values. This is just a result of an incomplete measurement. But what is an incomplete measurement? I mean, when we describe the standard procedure, we think about instantaneous measurements. No experiment can do instantaneous measurement. It takes a finite amount of time. So a very simple way of understanding an incomplete measurement is that, okay, what happened if I stopped that measurement before that finite time I chose was finished? And that's an incomplete measurement. So you can imagine that if this signal to noise ratio here, which is determining this overlap, is set by some integration time in your measurement, then if I don't integrate for long enough, I'm going to get overlapping histograms. But if I integrate for longer, I'm going to get the previous situation. So now we're starting to connect signal to noise ratio here with the idea of incomplete measurements. Okay. So the question I'm going to try and answer is that if you have a situation like this, how do you interpret the result of the measurement? And more importantly, if the qubit, let's say, started with an equal superposition, what happens to the qubit state after such a measurement? Okay. So I am now drawing these two distributions as conditional probability distributions. I have relabeled them. So the blue curve here is the probability that you will get a certain voltage V, so the voltage axis here, given that the qubit is in the ground state, and the same for the excited state. And this is something we can actually measure in the experiment. We can prepare the qubit in the ground state, make a series of measurements, get that histogram, prepare the qubit in the excited state, make a series of measurements, get the other histogram. Let's consider a situation where I prepared an equal superposition. You start with the system, the blocks for you here, and then you make a measurement. Now making a measurement actually now means drawing from a probability distribution, which is the combined probability distribution of these two. Why combined? Because the qubit is in an equal superposition. So the result can be from either of those distributions. So what I have drawn here is the combined probability distribution of both of those curves shown earlier. You make a measurement, equally weighted average, because I created an equal superposition. Okay. So now I make a measurement, and that basically means that I pick a value along this axis. And there's a certain probability for that to happen. Let's say that in a certain measurement I got this value shown by the black solid line. Now because this value here is slightly skewed to the left and closer to the ground state, it means that the chances that the qubit actually is in the ground state are higher. So this is now a probabilistic interpretation of the result of an incomplete measurement. So actually it turns out that you can interpret what happens to the qubit just by using Bayes' rule of conditional probability. Because what is it you're trying to determine? You're trying to determine what is the probability that the qubit is in the ground state. You can equally define it for the excited state, given that I measured a voltage V. And that's just given by this conditional probability rule. That is, the given what is the probability that the qubit was initially in the ground state. In this particular case, it was 50%, multiplied by the conditional probability distribution for the qubit to be in the ground state, and then just normalized by the weighted average. So because I'm slightly skewed to the left, this formula will tell me that after that one particular measurement, my qubit is going to be found slightly closer to the ground state. Let's do this again. Now I have to update this conditional probability distribution because the weights of 0 and 1 have changed. And now I have slightly skewed distribution, which is now closer to 0, which means that there's a higher chance that if I now make a second measurement, I'm going to get 0 again. So let's say that that happens. This time I get this value. You update the state again. The state goes up, and you move it again, and so on and so forth. So now you can see that the process of measurement can actually be broken down into incomplete measurements, which together result in a complete measurement. And when is the measurement complete? In this picture, the measurement is complete when that vector has either progressed all the way to 0 or all the way to 1. And then this formula will tell you that it will no longer update, because this and this will become equals. You will get basically the same result and again. So you see that the QND idea that once the system ends up in an eigenstate, it will remain there, and the result of the measurement will emphasize that. But there is a piece of information I'm not telling you here, and I don't have time to explain today, is that if you do this right, in the sense that if the measurement only measures this sigma z, or the fact whether the qubit is in the ground excited state, then there is actually no loss of information, and the state remains pure. Yes, we have extracted all the available information. We have not lost it to some uncontrolled degrees of freedom. So because we started in a pure state, what I did was a very deterministic, it was a random process, but I know exactly what happened. So when I update the state remains pure. Okay. Well, the result of the measurement tells us. So now there's a catch here, which some people might have noticed. I started with a known initial state. I knew that the system was in an equal superposition. This is not the standard situation when you actually make a measurement. If you already know the initial state, there is no need to make a measurement. You know everything you want to know about the state. So typically when you start with an unknown state, then you cannot draw that block vector here anymore. Your best guess is actually a mixed state with equal probability of 0 and 1. And then what happens, as you acquire information, the length of that block vector slowly increases. That corresponds to the acquisition of information, and the purity of the state increasing till it ends up in the eigenstate where it's now a completely pure state. Okay. So the general idea I want to sort of convey here is that a weak measurement is just an incomplete measurement, and a sequence of weak measurements, as we showed, completes the measurement and results in what we typically understand as projective measurements, where the system ends up in the eigenstate. Okay? So here's a quick movie of this process. There are two vectors here, the red and the blue. The red is the situation where I knew the initial state. The blue is the situation where I did not know the initial state, so I just used a mixed state. And I'm doing a sequence of weak measurements and updating the state. So this process is completely random, because we have been told that if you make an equal superposition state, the result that the qubit will end up in 0 or 1 is completely random. And it is. You see sort of a random walk before the system ends up in the eigenstate. But the important thing is that if I actually do this measurement right, I know what random event happened, and I can have complete knowledge about the state of the qubit all along the process. So this is what I mean by in the title, the evolution of the quantum wave function. It's important that you know the wave function in the beginning to have a pure state all the way, and the measurement has to be 100% efficient in order to maintain the purity, which means that all the available information you can access.
Does it matter to you whether it's an ensemble measurement or a single state measurement?
So all of these measurements are done on individual quantum systems. The ensemble is essentially created by repeating it with identical conditions. So if you had an ensemble of systems, then each individual element in the ensemble will undergo a different random perturbation, but you have to then keep track of that. So this is essentially being able to track the degree of the wave function of a single degree of freedom. So again, emphasizing that tracking is only possible if the initial state is known. Otherwise, you just slowly project towards the... Can you do this in NMR? I think the measurement in NMR is nowhere near the efficient as what we are describing here. And you need to be able to access a single degree of freedom, or if you have many collections, you need to be able to know exactly the result of the measurement of all of those. So I think the simple answer is no. You need individual degrees of freedom. Yeah. That's an excellent question. It's completely random. If the first measurement pushed you towards the ground state, there is a higher probability that it might end up in the ground state. Oh no, like one of them ended up in the lower hemisphere, the other one ended in the... Is that true? Let's play this again. I mean, that's just the particular sequence of random events I chose here. Yeah, but there it crossed the hemisphere up and down. So it's a completely process given, and the result of the next measurement is exactly given by the formula I displayed. So there is a random aspect to it, but with a weighted probability distribution. So there is no reason that if it started moving up, it will keep moving up. In fact, there can be situations where it can reach almost all the way to 0 and then turn around. There's a finite probability to do that. So I like this cartoon here, which kind of explains what is really the problem of achieving this kind of a measurement. So in this cartoon, I call this the game of telephone in Schrodinger's farm. The little duck here is my delicate quantum object, and the man here is sort of the classical experimenter who is trying to figure out the quantum state of this duck, or the message the duck has said. Now, the man is most comfortable talking to its classical counterpart, the cow. So, when you make a measurement, he asks, okay, tell me what the duck said. But of course, the cow just says moo, because a lot of stuff has been lost in translation. And what I'm going to tell in the rest of the talk is how we managed to get the message of the duck all the way to the man with the least amount of contamination. And that's really sort of the challenge in the measurement, and we have finally been able to sort of reach very close to this idealized limit. I'm going to go very quickly through the rest of the slides because Steve did a good job of introduction. The qubits are essentially nonlinear oscillators. Here's the Josephson junction. Now I have two in a loop. That actually allows me to tune the energy levels. This device is called a squid. It's shunted with a capacitor, and then you have a cosinusoidal potential, which is an unharmonic potential. The levels are now unequally spaced, so you can have tunable frequency. And for comparison, here is the equivalent harmonic oscillator. So you see that each level is subsequently lower. That allows you to selectively address the lowest two levels. This very basic simple circuit was invented at Yale several years ago now. It was called the Transmode qubit. The measurement architecture, as Steve explained, is the cavity QED. You take your nonlinear oscillator, which is the qubit, you couple it, here in this case so shown with capacitors. This is the circuit diagram equivalent with an linear LC oscillator, which is the harmonic oscillator. In atomic language, you have a Fabry-Perot cavity with an atom inside. There are these characteristic rates, the rate at which the photons leave the cavity, kappa. That here is controlled by the capacitance here to the outside world. This is where the microwave transmission lines come and connect. The coupling between the qubit and the cavity is set by these capacitances, and that controls the rate G, which is the rate how the atom exchanges excitations with the photons in the cavity. And you want to be in a situation where this G is significantly greater than kappa. That's the strong coupling limit. For the measurement part, you actually don't really have any such strict restrictions. You can do the measurement in various regimes of G and kappa. So this is the dispersive Hamiltonian qubit Steve also showed. There's your spin-a-half qubit. This is the resonator Hamiltonian. I have written it specifically to emphasize the measurement aspect, that the resonator frequency is now modified by this dispersive shift chi and the state of the qubit, and that's essentially the way we can probe the state of the qubit. We probe the cavity state, and that tells us about the qubit state. Okay. So essentially, the cavity frequency is a function of the qubit state. Now, this is the architecture. Steve had also mentioned this. I like to call this the artificial atom in a real cavity now, because we have moved from designing microfabricated LC circuits on chip to just a waveguide cavity. This is just a hunk of aluminum machined in a regular machine shop, and it gives amazingly high Q for quality factors. For these experiments, we actually did not really need those high Qs, because we are primarily using the cavity as a measurement tool, and in fact, you want low Qs, but low Qs not due to the internal dissipation, but to the fact that I couple them quite strongly to the environment, which is where the signals are coming out, so that I can make the measurement quite fast. And that's important for these experiments. This is the 3D transmode architecture, the Josephson junction with these big dipole antennas coupling to the cavity. Again, a milestone achievement at Yale. And these numbers are just getting better and better. I have to keep updating this slide every few months. As Steve said, now the T1s are near 100 microseconds, and T2s about 150 microseconds. 5-6 orders of magnitude improvement in the last 10 years, which is fantastic improvement. And the real nice thing here is that this is a robust and modular design. Steve had showed a big chip here sitting in this slot. You can make a small chip, really doesn't matter. You can have several of this chip. If the chip doesn't work, you throw it out, put a new one in. It has sort of changed the way people are doing this experiment. And I want to sort of emphasize here, this is really the beauty of this architecture. It's so easy that if you have a new idea, you can go in, make a new design, come back, and do the measurement. And I think this is where we are different from, say, atomic physics approach, which have done amazingly in the last 20 years or so. And of course, the Nobel Prize for 2012 were given specifically for developing techniques to address individual quantum systems, but we are now catching up really fast. The difference here is that these are artificial systems. They're not real atoms, but they come with the advantage. Yes?
You listed a bunch of things that don't matter. When you make them, they all come out the same no matter what you've done.
Oh, the qubits? No.
No, the cavities.
The cavities, well, so for this particular case, what matters is that the rate at which I'm coupling out is significantly larger than the rate at which photon dissipates, say, to some other unknown loss. What that means is that I'm collecting almost all the photons which are available.
How do you do that? How do you design it?
So the way you design is that the properties of the aluminum and how we prepare the surfaces and things like that, usually if you don't do much, just go machine and clean it in regular soap water, rinse it in alcohol, you can get Qs of several 100,000 just of this was basically what caused this architecture to succeed immediately. Somebody went in, machined this thing, came out and said, oh, 100,000. This was pretty good. If you work a little bit, that's without the sapphire plate. Yeah, when you put the sapphire, well, for superconducting qubits, it's quite remarkable given how we have been progressing. But as you saw from Steve's results, by designing this box a little bit better, making the edges nicer, and then playing with the shape of the cavities, there are various tricks to minimize the effect of the different sources of losses which can affect the Q. No, the SMA connectors is what controls how I'm coupling to the outside world. So in this case, the SMA connector sticks into the cavity sufficiently that the total Q is only a few hundred. I think in this particular case it was 400 or 500. But you have to be this very, very important part. This Q does not represent a loss. It's the loading. I have intentionally coupled to the system so that those photons which are leaking are not going into the void. They are coming towards my detection system, which means I collect every piece of photon which is available to measure. Yeah. Yes. That's right. That's a very good question. The thing in this case which determines the critical current is the area of overlap. Nanofabrication allows you control to say 10 nanometers on an edge very easily. Usually, if you are careful about the standard protocols, you can easily get it within 5%. Okay. Yes. See, and depending on the experiment you're doing, if you're imagining some large-scale quantum computer kind of thing, hundreds of qubits, you might imagine that you need to know every one of them precisely in advance, otherwise it'll be a problem. For very basic quantum physics experiments like this, I don't really care what frequency it turns out. If it's off by 5%, I just go measure and I find out. Yeah. No, so that's the number. That's the number. Now, if it was 500%, this would be big trouble. Now, Josephson junctions made out of aluminum are extremely robust, and as Steve said, there is a correlation with the room temperature resistance of the tunnel junction. Yes, but you put it in the evaporator under identical conditions for the same amount of time, and it works really well. And another thing I would point out is that if you make a squid loop, then you can then tune it. You can actually tune the Josephson energy, and in fact, that's important for several experiments. Okay. So let's talk about the measurement very quickly. The idea of mapping to point to states. Steve had shown the extremely strong coupling limit where the resonant frequencies are quite far away. Here, the frequencies are maybe only separated by about a line width or so, and we always typically measure the phase to measure the resonance. That is, we send microwaves, they reflect off, and the phase of that reflection depends on the relation with the detuning from the resonant frequency. So these are two resonance curves. The resonance is right in the middle of the point of maximum slope. One shown for the ground state and one shown for the excited state. So if you bias right in the middle where they have maximum separation, what you get is a phase shift which is dependent on the qubit state. That's essentially the measurement. You can sort of map these phase shifts into these phasor kind of pictures. In the IQ plane, you have now two vectors with different angles, and the information is actually contained in only one quadrature. Because if these vectors of the same length, then this projection here on this axis, I-axis, is the same for both the states. So it actually contains no relevant information about the qubit state. So this is actually important because we can now we have a way to selectively measure only this quadrature. And that allows us to reach this idealized limit where the only piece of information that is available is about the qubit state, and we are able to acquire it. Okay. So what sets this measurement strength or that separation of the histogram? It's the phase shift. Well, the larger the phase shift, you can think that there is more information per photon, but it's also set by how strongly I'm actually driving the cavity. Because if I drive the cavity stronger, then these vectors are much bigger. So it's really a separation in phase space of these two vectors which determines how strongly I'm measuring. So we now have a way of tuning this measurement strength. I just turn the measurement microwave power low, and then I reach the situation where these histograms are highly overlapping, given a certain integration time. And I can tune that. Yeah. And the noise in the ideal case is set by 0-point fluctuations, and it's really the signal to noise ratio. This is sort of a concept can be difficult to understand in the beginning, but it's really the SNR which matters. It's not the signal and the noise independently, but it's the ratio, provided that both the signal and noise are set by some fundamental properties of the system. Okay. The problem really in this experiment is that this power typically is 1/10 of a femtowatt. And we need like milliwatts of power in order to drive some room temperature electronics. So we need 12 orders of magnitude. And how do we get that? I mean, we use commercial amplifiers, but there's a critical piece which was missing till about a few years ago was the superconducting parametric amplifier. Because these commercial amplifiers actually will amplify, but they will contaminate the signal with a lot of noise. And that basically disturbs this balance of this careful balance between the signal to noise set by the measurement and the noise coming from the technical difficulties in your measurement chain. So the parametric amplifier very quickly is just again a nonlinear oscillator. You look, the circuit looks exactly the same. There's only a difference in the parameters. The critical currents are about 100 times larger. The capacitance are also 100 times larger. So it looks more like a classical oscillator. It means that it has a very large potential well with many, many, many levels rather than the few levels as in a quantized system. Okay? And such a nonlinear oscillator has a typical nonlinear response where these resonance curves, where I've plotted oscillation amplitude as a function of frequency, sort of bend towards the left because of the softening nonlinearity. And the idea is that if you bias sort of very close to one of these very sharp transition points, that acts as a very sensitive amplifier, and you can actually increase the size of the signal. And more importantly, in principle, you can do this without adding any noise when you're measuring that single quadrature. So what this allows us to do is to increase the size of the signal by about a factor of 100 without contaminating any further, so that we can now use commercial systems which do add some noise, but now the effect of the noise has been reduced significantly. Okay. So here's the full setup. I'm going to sort of skip over the details. Here's the qubit plus cavity. Here's the amplifier. This will be sort of drawn for the planar version, but it doesn't matter. The signals come here. They propagate to the amplifier, where they get combined with a strong pump which biases the system to the right point, and then the amplified output goes this way, and then you can detect that. All is done at very low temperatures so that only 0-point fluctuations dominate. Essentially, as Steve was saying, 21 gigahertz is about a Kelvin. So when we are at 30 millikelvin or so, we are much below the quantum 0-point.
Question?
Yeah.
About the in-principle noiselessness.
Yes. Yes.
Go back one slide.
Yeah.
You have a squid loop on the right in purple.
Yes.
No, fine. I'll
Yeah.
talk about it.
Yeah.
You have a squid loop in purple.
Yes.
Which is an open loop that is sensitive to fluctuations in that temperature.
Absolutely.
And if it sees an environment at some temperature, that presumably there's black body radiation in that environment at that temperature, something like that. You don't really
Yep.
produce noise.
Yes.
So is that device quieter than the ambient noise temperature of whatever black body?
Yes. The flux noise or a magnetic noise in a squid can be made very small by just making this loop very small so that it's less sensitive. And these squids also have inherent fluctuations. It's called the 1/f flux noise. What we have seen is that they don't affect the noise temperature, beyond the percent level. And in fact, we haven't really looked into much more detail than that, but it's not a problem. And I can explain that maybe at the end of the talk. I have some additional slides about the noiselessness aspect, but I think I really need to rush to finish this up. So doing this technique, we were actually able to first observe these so-called quantum jumps. You prepare the qubit in the ground or the excited state. You make a measurement. Here are 3 traces. The blue one was prepared in the ground state, and the red and the green was prepared. One single measurement trace, no averaging going on here. You can see that just in about 50 nanoseconds or so, you can separate the 2 signals quite well. It means that you have real-time information about the state of the qubit. You keep watching for a little while longer, the excited states drop back, and you can see them in real time. This was one of the experiments for which Dave Wineland got the Nobel Prize in 2012, and 20 years later, we have been able to do this in superconducting qubits. But I think it represents a very significant advancement in what we are able to do in terms of control and measurement in these artificial quantum systems. So these were, of course, quantum jumps due to spontaneous decay. I'm ashamed to show this data because the characteristic time here is only 300 nanoseconds. It was a couple of years ago. Since then, we have learned much more on how to make better qubits. But in this experiment, we are not concentrating on the qubit lifetime. So I can say that this is not a bug, it's a feature. Even though the lifetime was so low, I was still able to measure it because my measurement is really, really good. Okay. So this is the weak measurement where I don't control the microwave power, make it weaker. And these are now measured histograms of the ground in excited state. And what's plotted in green is the conditional outcome. I make a weak measurement, and I bin all of the measurement results based on the value you get. And then I do a strong measurement to figure out what happened to the qubit. And what you see is that as the results of the measurement are skewed towards the red, the qubit starts to go towards the excited state. That's the conditional state probability going towards 1, and vice versa. So, and in fact, this curve maps very nicely to that formula I explained. And if you make the measurement slightly stronger, you see that this curve now is steeper. The histograms are slightly separated. So the measurement now is stronger. There are some excellent results from Professor Michel Deveray's group at Yale. I think it's going to be published in a few weeks, who have done more careful analysis of this process using a slightly different kind of an amplifier. And I encourage for people interested to look out for that paper. It should be coming out soon. The last bit is about quantum feedback. I'm kind of running low on time. But basically, the idea is that if you now excite the qubit at its resonant frequency, it undergoes these what we call Rabi oscillations. It goes from ground state to the excited state continuously. And if you just do that and don't measure, then there is sort of a steady rate of Rabi oscillation. The block vector goes around at a steady rate. But if I now try to measure it using these weak measurements simultaneously on at the same time, then these measurements start developing some hiccups. And the reason the hiccups are coming from the fact that the measurement is giving you some output, and that's reacting back on the qubit. Here are two separate iterations, and then you see that over time they sort of become completely out of sync, which means that the phase is getting randomized. And the idea of feedback is that can I track this and do something to undo this effect? And sort of doing a full computational tracking, like using the probability formula, is actually very intensive, and several labs are working to develop the technology to be able to do that. But there was a nice trick proposed by Sasha Korotko at Riverside, that in this particular experiment we can actually use the oscillatory component. Because this is constantly oscillating at a roughly constant frequency, we can actually look at the oscillatory component. Here's a measurement of a spectrum of that oscillatory component as a function of different measurement strength. The blue is the weakest and the red is the strongest. So you see that the width of this spectrum is increasing because of the fact that the stronger I measure, the more I'm disturbing. So it's sort of affecting the oscillations more and more. So what we do now is, you imagine that the measured output kind of looks like this. This is really a cartoon picture. You cannot really observe this in such clarity. But the idea is that you have a noisy oscillatory signal, and you now use a reference signal which has roughly the same frequency. And you can use the idea that if I multiply the two together, you get an output which is proportional to the phase difference. Now we use that phase difference as the error signal, and then use that to control the frequency of the qubit, which we can do by just controlling the magnitude of the power we are sending to the qubit. So people familiar with control electronics will immediately identify this as a phase lock loop. And it's basically a phase lock loop where there's a quantum object, and then there's a classical loop completing the overall feedback loop here. So here are some Rabi oscillations which, without any feedback, they decay. And I must emphasize that here the decay is actually set by the strength of the measurement, not due to the intrinsic decoherence, which also causes decay. The measurement rate is significantly stronger than the intrinsic rate. So here's the width, that spectrum again. You see it has a characteristic with gamma. If you plot gamma as a function of n bar, which is the number of photons, strength of measurement, you get the expected nice linear relationship. And there's an offset, which is the environmental decoherence. So you work somewhere up there where the environmental decoherence is sort of not the dominant thing disturbing the qubit. And now we close the feedback loop, and these oscillations get locked to the reference signal, and they no longer decay. In fact, they keep going for as long as we measure. Our experimental protocol sort of allowed us only to go out to a millisecond, but essentially they are locked forever. But there's an efficiency factor, which is that what is the contrast of these oscillations? And that's actually only about 50%. We can do quantum state tomography to verify that these stabilized oscillations are really quantum, and I'm not measuring some spurious signal leaking out of my system. So this is showing the different block vectors as a function of the duration of an oscillation. You see that the y and the z components are oscillating, while the x is constant, which is what you should expect for rotation around the x-axis. And the feedback strength also controls this efficiency of locking, and we find very good agreement with numerical simulations to show that we really understand what's going on. The efficiency here of 45%, which basically tells you that it's not perfectly locked. The reason for that is there are two main reasons. One is that there's a delay. by the time we measure, do all the processing, and send the signal back, just the length of the cables introduces about 100 to 200 nanoseconds, and that disturbs, the correction is not perfect. And also, there is actually significant loss between the cavity and the amplifier. We have independently verified that the amplifier itself is adding very small amount of noise, but because of the microwave components in between the amplifier and the cavity, a part of the signal gets lost, and that's the dominant mechanism, and we're working hard to sort of improve that. And in principle, it's possible to get close to 100%. Just to, yeah, I'm wrapping it. So I'm going to skip through this. There are different kinds of back actions you can measure, and essentially go to the conclusions. Demonstrate a weak measurement, which allows us to sort of do high fidelity monitoring. We stabilize Rabi oscillation, and the things which are limiting the efficiency are technical problems. In principle, we can fix them. And there's a whole slew of sort of experiments which are now opened up, which is basically measurement-based quantum control. We need to fix the efficiency, but now you can not only stabilize oscillating states, but you can stabilize stationary states on the block sphere. As Steve showed, that you can now measure the cavity using a qubit plus cavity. So you can kind of do the kind of experiment Serge Haroche has done on cavity. Now you can use these parametric amplifiers to make high fidelity measurement and even feedback on a cavity and create more complex states using these ideas. And then you can now extend these to multiple qubits and then actually create entanglement between qubits which are remote, but the only connection is a common measurement between the two. So quickly like to thank all the members of the Quantum Nanoelectronics Laboratory where this work was done, and a quick advertisement for the new lab at TIFR, the $1 million view, fantastic, beautiful campus. This is my rendition playing around with Google SketchUp of what the lab might look like. And please contact me if you're interested, postdocs and graduate students and short-term projects. There are excellent facilities at TIFR for making all of these kind of devices. The fabrication already exists. The cryogenics and the microwave tools are coming shortly. Thank you very much.
We are running out of questions, but we will certainly have. You know, there is Auditorium type measurements where you can measure momentum and coordinate at the same time, respect at the same time.
Yes.
And they are fundamentally different from measuring wound observables. So I was wondering whether you can also do this kind of study yourself.
Yes, so this is something I skipped over in the end. It turns out that choosing the quadrature is kind of like choosing the axis of measurement of the spin, whether you decide to measure sigma z or sigma x, and that changes the back action. And then one really interesting experiment is that if I decide to use my amplifier to only measure the quadrature, which is perfect, completely orthogonal, I don't learn anything about the qubit state because there is no information there, which means that actually nothing is happening to the qubit along the sigma z axis. So in some sense, I have kind of erased the measurement. It's a little bit tricky. I introduced photons so to start a measurement, but by processing those photons in a different way, I have sort of undone that effect. But something does happen because measuring this quadrature actually amounts to measuring the photon number. And because these are coherent states, those photon numbers will fluctuate. Fluctuating photon numbers give you fluctuating qubit frequency. So that actually causes a random motion along this axis. And that, in principle, can be corrected using feedback. So, you know, it kind of changes the notion of what actually constitutes a measurement. When circuit QED started, you had a simple picture. I introduced photons in the cavity. That's what did the measurement. But that's not the end of, that's not the complete story. You have to sort of go through the line and say exactly what you did to those photons, because that precisely determines what happens to your qubit. So, absolutely, these kind of experiments are sort of being planned for the near future.
I have a question.
Yes.
The non-decay of the Rabi oscillations, is it equivalent to quantum Zeno effect?
Not the non-decay. The quantum Zeno effect actually is this particular idea. If I measure strongly and drive at the same time, then the driving of the qubit is trying to make it rotate, but the measurement is now forcing it to be in one of the eigenstates. So you actually pin the states to be in the ground excited state, but the Rabi drive is trying to change it. So essentially you slow down the evolution, and that's the essence of the Zeno effect. The original Zeno was sort of talked about completely freezing the state. That, of course, is not really possible. But this effect we have observed, where we drive the qubit and make strong measurement, and we basically observe telegraph-like noise. And this data is actually being processed to be written up. So the stabilization is a slightly different idea. Yeah.
Yes, yeah.
the weak measurement data that you have,
Yeah.
Was it a histogram of the voltages or currents or whatever that you mentioned earlier?
That's right.
But what does the y-axis signify? The values are too small, right?
So the y is the probability. I have normalized by the total number of counts. So it's the probability distribution. I repeat these measurements many times with the qubit in the ground state, and I construct that histogram. So this is just normalized probability. So you divide by the total number of counts. The x-axis is just some random, some scale I have chosen to how I define my voltages, for example.
Okay.
Thank you. Oh, thank you very much.